Okay. So the plan for today, like I said, is to do, so to start with some CNF CYK exercises, and then also to talk about some exercises that use the pumping lemma for context-free languages. So the first thing that we're going to look at is just that. So this is a question from problem set 3. So this is going to be question 3A. Apologies for not printing the problem set. My department started asking me why I was printing so many things. And, it was a bit hard to justify that I had to print problem sets for every student in the tutorial. Question 3A is the following. So it asks to convert the following grammar into Chomsky normal form. Okay, so the grammar is the following. So it's S gives you BS, AA, AC. A gives you AA, hello, AAB or epsilon. B gives you ACBB. Okay, so we want to convert this grammar into Chomsky normal form. Remember, Chomsky normal form, a grammar is in Chomsky normal form if all of its production rules look either like, this, or this, or like a mix of 1 and 2, right? Okay, so how do we do this? The way that we start with the grammar and then convert it to Chomsky normal form is we first have to sort of do grammar simplification. It's a bit of a misnomer to call it a simplification because sometimes it actually makes the grammar more complicated, but that's just how I'm going to call it. And grammar simplification includes 4 main steps. So you want to remove epsilon production rules, So production rules like this. You want to remove unit productions, So production rules like these, right? Then you want to remove non-generating variables, so variables which never generate just a sequence of terminals. And you want to also remove, so there should be a sort of remove thing here, a remove verb. And you also want to remove unreachable variables, so variables which you cannot reach from the starting variable. Okay, so we're going to do this one by one. And then the second step after you finish the simplification is to essentially convert to CNF using intermediate variables. Convert to CNF via intermediate variables. So if you don't know what that means, then I'll show you in a second. Okay, so let's first do the first part, the simplification part. So for simplification, we first want to start by removing the epsilon transitions. So let's take the grammar. And let's say, okay, so step A here. So this is 1A essentially. So this is removing epsilon production rules. So I have my grammar here. Oh, paste image. Yeah, that's good enough. So I have my grammar here. And so how do I remove epsilon production rules? Essentially, you start with a base case, which is you find all of the epsilon production rules that exist in the grammar. So in this case, it's only A gives you epsilon. And then you apply the recursive case, which is, are there any unit production rules that allow your variables to also sort of indirectly or intermediary via this intermediate variable in the base case, the sort of empty string, right? So in this case, the recursive case would be, I can generate the empty string from A, but then I can also generate the empty string from S if I jump to A and then I go to the empty string here. So the recursive case is going to include this. And is there going to be another? No, that's going to be it, right? So we can see that this is the only other way that you can, the only other way that you can generate an empty string or epsilon, okay? So now that we've identified, so these are what are known as the nullable variables. That's what I'm going to call them. They're nullable because they can be replaced by the empty string. what I need to do now is I need to sort of account for the fact that one or more of the nullable variables could be replaced by the empty string on the right-hand side of the production rules, right? So that's what I'm going to do. The way that I'm going to do this, it would actually be very convenient if this was not an image, actually. So the way I'm going to do this is, I'm going to start with my, original grammar, and then first of all, remove the epsilon production rule, right? And now for every sort of right-hand side that contains one or more nullable variables, I'm going to replace sort of every possible combination of the nullable variables with epsilon, right? So the two nullable variables are a and s. So that means that here what I'm going to add is, so for the production rule of s, I'm going to say, well, s could be replaced by epsilon, in which case I would just have b on the right-hand side. So I'm going to add b. A could be replaced by epsilon, in which case you would just get A, right? So I'm going to also add A to the right-hand side. Technically, A here could be replaced by epsilon, but then I would add an epsilon production rule, which I don't want to do because I want to remove them, right? So I'm not going to do that. So that's good for this variable. For this variable, the only nullable variable on the right, the only nullable variable on the right-hand side is A. So if I replace A with an empty string, then I would get CBB. Okay. So this is G. So this is G minus epsilon production rules. Yes. Yes. Hmm. Yeah. So it has to be, okay, so the question is, because B here has on its right-hand side a production rule that has at least one nullable variable, then why isn't B a nullable variable? So nullable variable means that you can take B and you can replace all of it by the empty string, right? Which you can't really do here because on the right-hand side, you're always going to have a C, right? So it has to be something like unit production rules going from sort of the recursive case nullable variable to the base case nullable variable. So it has to be that way. Yes? Yes, so the side effect here is we're going to create a grammar that is equivalent plus or minus the empty string. In this case, minus the empty string. Yes, yes, yes. Good point. Nice. Okay, good questions. All right, so this is the grammar minus the epsilon production rules, right? So I've removed them. I'm very happy. Step 1A is done. Now step 1B is to remove the unit productions. Okay, so the unit productions, right? The unit productions are productions of the form A gives you B, where A is of course a variable and B is a single variable. There's nothing else on the right-hand side. So I want to remove these because I can't actually do anything with them when I'm at the stage of converting to Chomsky normal form. So let's do that. Let's make this all a single color. Okay, so the first thing that I want to do before I start removing the unit production, the unit productions is I want to see, what are the unit productions? So the base case here is, are there any sort of unit productions that I have just listed on my grammar? And the answer is yes. I have S gives you A and S gives you C, right? So I have S gives you A and S gives you C. Now, the recursive case is essentially if I had something like, if I also had something like, I don't know, A gives you, so this doesn't actually exist, but if I had A gives you B, right, then I would have A gives you B here as well in the base case. And then the recursive case would say, well, actually, that means that from S, I can go all the way to B, right, with just unit production rules. So then if I want to remove all the unit production rules, then I also have to add the production rules for B to S, right? So that's if B was actually there. But it's not, so in this case, I'm okay. So the recursive case doesn't actually add anything here, right? So now that means that I can remove the unit production rules. But of course, if I want the grammar to be, let's just remove them here, actually. if I want the grammar to be equivalent, right, then I have to kind of add back all of the production rules that, I can go to using A as the intermediate variable or using C as the intermediate variable. So I'm going to add, in this case, to the production rules of S, all of the production rules of A and of C, right? So the only production rule of A is A gives you AAB, so I'll add this here. And, C doesn't actually have any production rules here, so I'm not going to add anything to S, right? So now this is the grammar minus the unit productions, right? So I remove the unit productions, but for the grammar to be equivalent, I have to add back everything that I can sort of get to using those unit production rules that aren't unit productions, right? So that's the general idea. Yeah, question? Yeah. So like, I mean, if you did actually have stuff in the C here, right? Then you just take this stuff and add it here, right? It does. I removed it. Yes, yes. Nice. Yeah.
Sorry, you might have said this. You remove the C just because it literally doesn't.
No, you don't remove the C because it doesn't go anywhere. In fact, it does go somewhere, right? Well, I mean, this particular C.
Sorry,
Yeah. So I'm removing the C because, I mean, at this step, I want to get rid of all unit production rules. So C is part of that, right? Because I have S gives you C, that's a unit production rule, right? And the reason why I'm getting rid of this is because I want to get this to Chomsky normal form. Chomsky normal form is a binary tree, right? So like if I have something like S and then C, well, already I've sort of broken the binary tree sort of property of the CNF parse trees. Make sense? Okay, cool. Any other questions? No, okay, cool. All right, so this is my grammar without unit production rules. Very nice. Now let's remove the non-generating variables. Okay, so let's copy this. And let's paste it here. So remove non-generating variables. Okay, so non-generating variables are sort of a bit easier to identify. Essentially, a variable is non-generating if there is no production rule it doesn't have a production rule where the right-hand side just has a string of terminals, right? So, so for instance, B is non-generating because if I look at all of its production rules, you never have something like just a string of terminals. So what that tells you is that if from S you at some point get to B, then you're essentially stuck, right? You can never actually just produce a sequence of just terminals because you're always going to have a variable in your sort of intermediate form. So then you're never going to get a string of terminals. So then it doesn't contribute to L of G, right? Because remember, L of G is the set of strings over the terminal alphabet such that you can get to them in any number of derivation steps from the start variable, right? So this is not, the fact that I have a non-generating variable, that's not going to help me do that, okay? So if I look at my grammar here and I try to identify the non-generating variables, well, S is generating because, for instance, it has S gives you B, so that's a string of terminals. It also has, for A gives you AAB, that's a string of terminals, so that's also generating. But B doesn't, right? B always has at least one variable on the right-hand side of its production rules. So that means that I can safely get rid of B and nothing bad will happen, right? So then this grammar is the grammar when I remove the non-generating variables. Okay, you got a question? No question? Okay, nice. Okay, nice. So that's my grammar. Now the last thing I need to do is I need to remove unreachable variables. So a variable is unreachable if you create a sort of directed graph with all of the variables, and you make an edge. You make an edge if you can go directly from that variable to the other, right? So for instance, here I have two variables. I have s and a. S can go back to itself, and s can go to a. Now, a variable is said to be reachable if there exists some directed path from the start variable to that node. So in this case, all variables are reachable. I mean, S, just by definition, is reachable to itself. A is also reachable because you can get to A from S, right? So this is the path that you can take. So that means that I don't have no unreachable variables. Which means that my final simplified grammar, quote unquote, unsimplified, because it's not that simple, is this guy, right? So this is my sort of G simplified grammar. Okay. Oof. All right. Any questions about simplification? No questions. Nice. All right. Hopefully this is clear. All right. So this is the first of sort of two main steps in the conversion of the grammar to CNF. The second step is to essentially binarize the grammar, right? So you want to convert to CNF by binarizing. So what does this mean? The sort of binarized grammar in CNF should only have production rules that look like, the sort of terminal production rules. So I'm going to label these as like T sub A gives you A and T sub B gives you B, right? So these are kind of like the base case of your parse trees. And all the other production rules in CNF, for them to be binarized, they should have something like this form, right? So A gives you BC. Now, how can you do this if you have, n number of variables on the right-hand side? So I have x1, x2, all the way to xn. Well, it's a very nice trick, right? You just sort of divide this production rule into several different layers, right? Into several different levels, right? So you start with, binarizing A gives you x1 to xn. You do this by saying, well, let's introduce a new intermediate variable y1. So now I have A gives you x1, y1. And now I just have to binarize y1 gives you, I just have to binarize, y1 gives you x2 all the way to xn. Well, how do I binarize this? I use exactly the same process, right? So I create a new intermediate variable, y2. Then I get the production rule y1 gives you x2, y2. And then y2, I sort of recurse. And now I have to binarize this guy, right? And in the end, right, my base case is essentially when I'm going to be at, I'm going to get the index wrong here. I think it's going to be something like y of n minus 2 gives you x n minus 1 xn, right? Something like this, right? Now I'm sort of done binarizing. I have only production rules that have a pair of variables on the right-hand side, right? So this is how I'm going to apply this general process. So let's take the variable, the grammar. Let's paste it back here. Now, how am I going to do this? Well, okay, I need to introduce my terminal production rules. So TA gives you A, and TB gives you B. Why do I need to introduce these? Because now what I can do is I can replace all of the places where I have, a mix of terminals and variables. Because then if I do that and I replace all the terminals with the variable, then I can apply this general idea. So that's what I'm going to do. This TB is going to be replaced by, this B is going to be replaced by TB, this A by TA. I'm not going to do anything here, right? Because this is already in Chomsky normal form. I'm not going to touch this. AAB, this is going to become TA, TA, TB. And the same thing for this guy, right? So it's going to be TA, TA, TB, right? And now to binarize, I just have to introduce one additional intermediate variable. Let's call it x1. X1 is going to be for TATB. So x1 is going to be for TATB. It's going to be replacing TATB here and TATB here. Okay. And now this is a grammar which, if I go through it, I have binary production rules, or I have production rules which just have a single terminal on the right-hand side. So I'm very happy I have a grammar which is in Chomsky normal form. Okay. Any questions about this? No questions. Nice. All right. Okay, so that was the first part of this question. Remember, we're trying to actually solve a question from the problem set. This was question 3. What did I say? 3A. Okay. The second part of this question was, now that you have the grammar converted into Chomsky normal form, you want to parse it with the CYKS algorithm, right? So that's what we're going to do now. We're going to parse it. Parse the string W BBA with the CYKS algorithm. So by parse, I just mean sort of derive a parse tree if it exists. Using the CYKS algorithm. By the way, why do I call it the CYKS algorithm? Because actually it was invented by this fellow by the name of Ichiru Sakai in 1961, which was several years before the people that are named after the algorithm. Kind of sucks. Like, you don't even get a letter of your name in the algorithm that you invented. It's kind of unfair. Where is he from? Japan. Oh, that's why? Tokyo is a small city? Maybe in 1961 it was, yeah. Okay, so I'm going to do this, right? I'm going to use the CYKS algorithm. Now, in case you don't remember or you've forgotten already, how does the CYKS algorithm generally work? So how does CYKS algorithm work? Okay, essentially, it sort of works by building the parse tree of the string of W recursively in a bottom-up fashion. So this is a bit of a review. I'm going to just quickly remind you how the general algorithm works. At least I'm going to give you the general intuition. Okay. So, I say that the parse tree is built recursively. So what does this imply? It implies that we have a base case, and it implies that we have a recursive case, right? So what is the base case? Well, remember, I'm trying to sort of create a binary parse tree, right? So the base case of this binary parse tree that I'm building bottom up is the leaves of the parse tree, right? So how do I create the leaves of the parse tree if my string is something like sigma 1, sigma 2, ... sigma n? Well, I use the terminal production rules, right? That's why I have them, right? So I use the terminal production rules. So T sigma will give me, sigma 1. T is sigma 2 will also give me sigma 2, and so on. Okay. I mean, of course, it's also possible that I have other variables that generate the terminal, in which case I should also include them as part of the base case. So this is kind of the base case. So the leaves of the tree represent the base case. Represent the base case. And the recursive case is the sort of internal nodes, how you build the internal nodes. So the internal nodes are the recursive case. And how does this essentially look like? Suppose I'm trying to build this tree, right? So I have S here at the top. And, I'm at maybe this point of the parse tree, and I'm building it bottom up. Maybe this internal node is supposed to sort of represent this subtree of sigma 1, sigma 2. So then what I'm supposed to do is I'm supposed to say, I need to sort of consider every possible way that I can generate the string sigma 1, sigma 2, right? So in this case, the only way to do this is by having a variable A that, gives you the production rule T sigma 1, T sigma 2, right? So that's very easy at this part of the tree, right? It gets a tiny bit more complicated when you go slightly up, right? So if you're now trying to recursively build up the internal node for, say, sigma 1, sigma 2, sigma 3, then you have to consider two possible ways of sort of generating the string with the sort of binarized CNF grammar. So sigma 1, sigma 2, sigma 3, this is either generated by first generating sigma 1 and then generating sigma 2, sigma 3, right? So I already have these cases already sort of in my table, right? So this is a dynamic programming algorithm. Or I can build a sigma 1 to sigma 3 by building first sigma 1, sigma 2, and then concatenating it with sigma 3, right? So this is essentially how I'm going to deal with each of the sort of internal nodes all the way to S, right? So S is going to generate the string sigma 1 to sigma n using one of n possible cases, right? So what are the possible cases? Either you generate sigma 1 to sigma n by generating sigma 1, and then by generating sigma 2 to sigma n, or by generating sigma 1, sigma 2, and then generating sigma 3 all the way to sigma n, or, and so on until sigma 1 to sigma n minus 1, concatenating it with sigma n, right? And each of these are things that you should consider in your table because they've sort of occurred at lower levels, right? Because remember how dynamic programming works. It sort of works bottom up. Hopefully you remember this. And so that's what I'm going to do in the table for the parse tree. Let me do the example. Then it'll be hopefully clear. Okay, so let's try to sort of implement this intuition that I've just given you. Let's remind ourselves of the grammar. So the grammar in CNF is here. Okay, so the grammar in CNF is here. Whoops. Oh, CNF was already there. Whoopsies. All right. Okay, so I'm going to build this table, and it's going to look maybe a bit different. It's just going to be rotated a little bit based on, I think, what you're used to in the slides. But I'm just used to doing it this way, but it's exactly the same. So don't freak out if it looks a bit different from the slides. So I want to parse B, B, A. So to do this, I'm going to create a table, of course. What would dynamic programming be without tables? I mean, it wouldn't exist. And what I'm going to use is the sort of upper triangular part of this table. So I'm going to use this part. Okay. And essentially what I'm going to do is for the sort of leftmost cells here, these are going to be used for the base case, right? So for generating, if W is represented as sigma 1, sigma 2, sigma 3, then these sort of leftmost cells, these three, right, are going to be for generating sigma 1, sigma 2, and then sigma 3, right? Then these guys are going to be for going sort of one level up. So actually what's kind of going on is this table, if you look at it this way, is kind of like the tree. But I mean, this is kind of difficult to sort of do as a human, so that's why we do it horizontally. Okay? So we're doing the sort of second level. So we're going to find every way that we can generate sigma 1, sigma 2, and sigma 2, sigma 3. And then lastly, for this guy, I'm going to consider either creating the string using sigma 1 plus sigma 2, sigma 3, right? So you can see that that's this guy and this guy, or sigma 1, sigma 2 plus sigma 3, right? Okay, so the way I'm going to do this is, I'm going to start with the base case. I guess this could be a bit lower. Okay. Okay. So let's see, base case. What are the ways in which I can generate B? So I can generate B with TB and also with S, right? So I'm going to consider these two variables, so S and TB. The same thing for the second letter because it's also B. So S and TB is going to be in this cell. And then for sigma 3, how can I generate A? I can generate A with S and also with TA, right? Okay, so far so good. Yeah, okay, nice. Now, this is sort of the base case. This tells me which variables can generate sigma 1, sigma 2, sigma 3 respectively. Now, for this case, I'm going to say, well, how can I generate sigma 1, sigma 2? By sort of having a production rule which, is sort of a pair where the first element of the pair is from here, the second element of that pair is from here, right? So essentially I have to check, I have to go through every possible pair here and see if any of these pairs exist in the production rules that I have, okay? So let's see. Do I have S gives you SS on the right-hand side? No, right? Do I have STB on the right-hand side? No. Do I have TBS on the right-hand side? Yes, it's here, right? So that means that I can generate sort of at this cell by saying, S gives me TB and S, right? I'm going to use sort of lines here because it's like manageable, but at some point you're going to want to start using superscripts. The last case was TB. Do I have TB here? I do not, right? So that's it, right? I'm done this recursive case here, right? Okay, cool. Now what about sigma 2, sigma 3? Again, same idea, right? For sigma 2, sigma 3, I look at every possible sort of pairing of the variables here and here, and I check if I have a production rule with this on the right-hand side, right? So let's see. Do I have SS? I already checked this, and the answer was no. Do I have STA? No, I don't, right? There's no STA here. Do I have TBTA? No, right? And wait, I skipped one. TBS, yes, thank you. TBS, oh, I have TBS, right? It's right here. Okay, nice. So I have TBS, which I can generate with S, right? Excellent. Okay, so far so good? Yeah, okay. So now I've sort of created, I've considered all the possible, yeah, is there a mistake? TA, TB? I do, yes, but it has to be in the right order. Right, it has to be TB and then TA. Yeah. So that's a good point, right? It has to be, so the order really matters here. So order matters, right? TB, TA is not the same as TA, TB. This makes sense because one is generating BA, the other one is AB, right? So it matters which order you use. Okay, nice. So now we're at this final cell. And now at this final cell, right, a common mistake is to just do something like, oh, do I have SS? No, so I'm done, right? This is not the right thing to do because you have this sort of overlapping sigma 2 here, right? And you don't want to generate sigma 2 twice, right? You want to generate sigma 1, sigma 2, sigma 3. So the way to do this is by checking if I have anything with STB and S, or with S and then STA, right? So let's do this first case. Do I have anything with S and S? No, I already checked that. Do I have TBS? Yeah, yes, I do. So I have TBS, that's here and here. Nice. Okay, so then I found one case. Are there any other cases that work? Sorry. Yeah, we can stop here. Yes, but suppose I was very keen to find all the parse trees, but yes, for a midterm strategy, maybe you want to stop because you don't want to waste your time. SS, that's not there. STA, that's also not there. Okay, so then it turns out this is going to be the unique parse tree. So what is this parse tree going to be? Well, I can kind of sort of almost read it from the table, thanks to the fact that I use these lines, right? So the parse tree that I reconstruct is going to be S, TB, S, and then S is going to be TB, S, and then this TB is going to generate B, this TB is going to generate B, and this S is going to be used to generate A, right? And this works, right? Like this is a valid parse tree because it's, if we look at the rules of my grammar, then, I have S gives you TB, TBS, so that works. TB gives you B, S gives you TBS again, so that's cool. S gives you A here, so that's all good. And the yield of the parse tree is BBA, which is what I was after. So that means that I'm very happy. Let's go with you and then you. Yes. I see. Well, the question is, would it not be easier to look at the grammar and just try? I mean, I think maybe given that the string is pretty short, that's probably a good approach in this case, right? If you do an exhaustive search and if at some point you're only, like you can consider all the possible sort of ways of generating strings of 3 terminals, right? So you sort of exhaustively list those with the grammar, and then you say, well, I do have a way of generating it, so then I'm done. So that definitely works for sort of BBA, so it's something like this. But if you have a string of length, 1,000, and you have 20 production rules, then yeah, good luck looking at the CNF. I don't even think Prakash could have done that. Yeah. Oh, you have a follow-up, yeah, yeah. Yes. If you were to backtrack visually, yeah, so like this is the table representation. Really what's going on quickly is, if we try to do this bottom up, but just keeping the parse tree as the data structure, you start with B, B, and then A, right? So then you see, okay, which are the ways that I can generate B, B, A, right? So I can use TB, and I can also use S. For B, I can use TB, and I can also use S. For A, I can use, what did I say, S, or let's do TA and then S, right? This is okay? Okay. Now I'm saying, okay, at this point, right, how could I generate BB, right? So it turns out the only way to really do this is by using S gives you TB and S, right? Okay. Then for this guy, right, for generating this pair, right, B and A, the only way to do this is to do, the same thing. S using S giving you TB and S. Yeah. Now I'm at the root node, right? I'm at the root node, and I want to sort of complete the tree, right? So the only 2 ways that I can do this is I can say my my root node goes to this part of the tree, and then this part of the tree, right? Or it goes, right, so that's one option, yeah? Or it does, something like it goes here, and then it goes here, right? So that's essentially what I'm doing kind of here. Like the visual that I just gave you here is the consideration of all the cases here. Does that make more sense or less? I mean, it gets a little bit, can you do this? I think you might really run into some issues given the length of the string in the midterm. You may want to use the table because it gets messy if you have a parse tree. Okay. I don't know. Is it? Yes. How did we construct the tree? We. Oh. The lines are because, S, see this line here, S, TBS, that's because I have the production rule S, TBS here, right? So, S, this is a variable, right, in a grammar. So it's going to get replaced with the production rule. Yeah, it is, no? S gives you TBS. So then S, like if you want to represent this in a tree, right? This is a subtree where you have S as an internal node, and as the children, you have TB and you have S. Right? No? Oh. I don't know. We have the line from this, yes. These two lines, right? The lines go together because it's a, yeah. Because we have the production rule, S gives you TBS. Yeah, maybe. Okay. Okay, we can talk after if you want. Okay, nice. Yeah.
Just really quick, the fact that the quote unquote tree you drew at the very bottom isn't actually a tree, like it has what the over it.
Yes.
I mean that it's an ambiguous grammar.
No, it's ambiguous. That's a nice question. So the question is, does the fact that you have like overlaying things mean it's ambiguous? No, actually. This is like just going to happen inherently by design of the algorithm. Ambiguous, so the grammar, it would be ambiguous if, if there exists one string for which when you apply the CYKS algorithm, there's kind of like two distinct parse trees from S here. Yeah. So if you have ambiguous, so the CYKS algorithm gives you two distinct parse trees. For the same string. Cool. Nice. Yeah. Yes, only at the root. Yes. Yes, for ambiguity, yeah. If you want to check for ambiguity, like if in a midterm, the question is does this lead to ambiguity? Then yeah, you have to check all of them. Cool. If the question in a hypothetical midterm is given the string BBA, does this induce two different parse trees, indicating that the grammar is at least the one in CNF is ambiguous? Then you have to consider every possible sort of way of generating the string BBA from the root node, right? Because like at some point there was a comment, I found one way of deriving it, so I can stop. So that's true if I just want one parse tree. But if I want to check for this ambiguity thing, then I have to go through every single case. Yeah, exactly. Yeah, that's right. If I have like a different S, right, with like, in this case, it would have been if I have like S gives you S and TA, for instance, then this would have indicated ambiguity. Yeah, nice. Okay, cool. It's always just one question with you. Okay. How do we construct the tree? No, we have to take this offline. Sorry, I gotta move on. I gotta give you another question to do. Okay, but I'm happy to talk after. Yeah, you know this about me. I don't lie. Okay, this is another question of the same flavor from problem set 4. So it's going to be to convert the following grammar to CNF. So this is from question 4b. So the grammar is going to be the following. So I'm going to give you some time to do this one. Okay, this is the grammar. Let me just double check that this is indeed the grammar. Okay, so let's convert it to a Chomsky normal form. And by let's, I mean you try for a few minutes. How many is a few? Let's say 5. Probably a good amount. Okay. And if you're done, you can raise your hand and I will check.
For the CYKS,
Yeah.
is that fixed format or we can do it
You can also do the one from the slides.
like the base cases on
Sure. Yeah. It's all good. It's all the same.
TBE? There's no variable E.
Yes, indeed.
That's part of the.
It's part of the question. I can't answer that in the midterm though. You must realize this. No, it's on purpose. Again, I cannot answer that question in the midterm. I'm being nice here. I mean, man, you're giving away all the.
It's in the slides. Like it's in the slides and for example, like
Let's let everyone else figure it out.
maybe yes, maybe
Huh? I don't know what you're saying, dude.
not.
Maybe. Right. It's been 5 minutes. Time flies when you are converting to CNF, as they say. Okay, so let's try to do it together. If you're not done, you can either follow along or maybe try to finish and then check the final answer. It's up to you. So let's do this. I'm going to go slightly faster, not explaining every single sort of concept again. So to convert to CNF, remember I have two things to do. The first thing is to do the simplification. So let's remove the epsilon production rules. So let's look at the grammar. And now let's look at what the nullable variables are. So the base case for the nullable variable is, S gives you epsilon, C gives you epsilon, and that's it. Yeah, those are the only base cases. For the recursive cases, we have, let's see. So the easy way to maybe do this is by creating a graph, which is directed and which has an edge only if there's a unit production rule from the variable to the other. So I have S, I have, let's see, A and B. These both go to C. C is nullable. Let's see. D goes to A and B. Okay, so it looks like this is my graph. If it's the directed graph of unit production, so this is it. Then I can sort of quickly see what the recursive case is. C and S are nullable variables, but now I also have that A, B, and D are also nullable, right? So I have that in one or more steps. I can generate the empty string with each of these variables. So it looks like it's all of the variables except for E. So that means that I have a bit of work cut out for me. So let's paste this here again. Let's remove the epsilon production rules. And now let's consider every possible replacement of the nullable variables at all of the sort of production rules. So here, this A, it's nullable, right? So it could be replaced by the empty string. So I have AA. The B could also be replaced by the empty string. So I have BB. I mean, C here could be replaced by the empty string, but that would just add back an epsilon production rule, which I don't want to do. For CDE, this one's nice, right? Because now I have two nullable variables. So now I have to consider the case where C gets replaced by the empty string, D gets replaced by the empty string, and both get replaced by the empty string. Okay. And then lastly, I have this production rule, but again, if I replace any of these by the empty string, then I add back the epsilon production rule. So that's not going to be good. So then it looks like this guy is the grammar without any epsilon production rules. Okay. So hopefully everyone is convinced by this. So now let's take this grammar and let's remove the unit productions. Okay, so let's remove the unit productions. So to do this, I'm just going to use the sort of graph that I sort of made above, but adding a few additional transitions. So, what are my unit production rules? So the base case, I mean, I could do the base case, which is, A gives you C and B gives you C and D gives you A. And then D gives you B. So then, you could technically read off this and do the recursive case. I think it's probably easier if you have a graph. So you have something like, A gives you C. I guess technically you also have C gives you E. So if C gives you E, you have, let's see, D gives you A, and also D gives you B. And then B gives you C, right? Yeah, okay. So that means in addition to the base cases, I have that, let's see, D can give me C, right, and E, right? So that's additional recursive cases. So D can give me C. D can also give me E. What else? Yeah, I mean, that's about it. I mean, there's A gives you E, of course. Okay, so I mean, there's the ones with E, but they're maybe not going to be that helpful. Okay, any others? No. Okay, nice. All right. So these are all of the unit productions, right? Along with the sort of recursive cases of them. So to remove them now, I take the grammar. So I copy this grammar, and I paste it. And I remove the unit production rules, adding all of the production rules of the corresponding variable that I'm removing, right? So maybe I shouldn't have done it all at once. So I removed C from A here. So that means that I have to add back everything that C gives me. So I have to add C, D, E, D, E, and C. I removed the B gives you C here. So I have to add back the C, D, E, D, E, and C, E. So C, D, E, D, E, and C, E. Here I removed C gives you E. So then technically I would have to add the things that E has, but E doesn't have anything, so that's nice. And then here for D gives you A. So here I removed D gives you A and B. So that means I should add back the things for A and B. So A, C, D, E. So this is the stuff for A. I mean, the stuff for A, for B has some repetition, so I'm not going to add duplicates. I'm just going to add the stuff that's different. So that's just going to be B, right? So this is the stuff for B, okay? Okay, cool. So this is removing the unit productions. Yeah, okay, nice. All right. Now, this is the grammar I have so far. It's sort of quote unquote simplified. Let's simplify it a bit more by removing the non-generating variables. So the non-generating variables are, well, I mean, technically E is a non-generating variable because, if you get to E, then you don't generate any strings of terminals. And then the other non-generating variable, let's see. So S has a string of terminals on the right, so that's generating. So there's A, so there's B, so there's D, but C does not, right? So that means that C is also non-generating. So that means that the grammar here, I can take it and I can remove all of the production rules that contain C or E or both. So I take this grammar and I remove the production rules with C or E or both, C or E or both. Of course, I remove this one, and then I remove this one.
How is the C non-terminating?
How is the C non-terminating? Because it doesn't have a production rule here where it just has strings of terminals.
Like similar.
Yeah. Like just a little. Sure. Yes. That's right. Okay. So now this is my grammar without the. Yeah. Is there a mistake? Aha. The question. No, because so the question is, can you do non-generating before unit productions? No, because maybe when you do unit production rules, you introduce non-generating. So it's possible you add more non-generating. So there's a very specific reason why it's in this order. Yeah. So notice also the reason why you do epsilon production rules before unit production rules is because epsilon production rules introduce additional unit production rules, right? So that's also why you have to do it that way. But yes, good question. Okay, so that was removing non-generating variables. Now let's remove the unreachable variables. So let's just create a reachability graph. So from S, I can go to A and I can go to B, and then D is all alone here. So D is unreachable because there exists no directed path from S to D, but A, B, and of course S are reachable from S because there is a directed path from S to each of those variables. So that means that I can, so D is unreachable. So that means that in this grammar here, I can now also remove anything that contains D, right? So I can remove all the production rules of D and all of the production rules that use D, but in this case, I don't have any. So then this is the sort of simplified grammar, which in this case is actually simpler. So that's nice. Yeah? The end of step one? Yeah?
So for C,
Yeah? Yeah?
all SCAB null. So we should also consider a possibility where you have both D and A, B epsilon and C, both C and E are nullable, so you have like an extra possibility for production.
We're talking about this one, yes?
Yes.
I
remove the epsilon production.
Sure. So I remove epsilon here, so I get DE. I remove epsilon here, so I get CE. I remove both, so I get E. What's the other?
For example, also remove D and E.
Is E is not nullable.
Uh,
Yeah. If E was nullable, then yes. Yes. Yeah, good point. All right.
exactly define it.
How do you what, sorry? Nullable variable? Well, a nullable variable is defined recursively, right? So the base case is that it's a variable for which it has a production rule that has only epsilon on the right. And then recursively, it's a variable which has a unit production rule to one of those variables. Yeah? Okay, nice. Okay, excellent. All right. So this is our simplified grammar. It's not yet in Chomsky normal form. So let's convert it. Actually, a nice exercise for you is at this point, if you take the grammar G, what is L of G? So the answer may or may not surprise you. I won't answer it here, but think about it. Now, if I take this grammar and I convert it to CNF, then I need to do the steps that I presented before, so binarizing the grammar, right? So convert to CNF. So to convert it to CNF, I have this grammar. In this case, in this very, very special case, I don't actually have to introduce the terminal variables TA and TB because I already have variables for which they only produce that corresponding terminal, right? In any other case, I could not actually do this. So if I had something like A gives you A or AB, right? Then you can't say because A gives you A, then I can use this variable as the sort of same as T sub A gives you A, right? Why? Because, if I start taking A and replacing the terminals with the variable A, then I'm introducing false generations that don't actually exist, right? So in this very special case, no need to introduce TA and TB because the only production rule of A is A gives you A, and the only production rule of B is B gives you B. Okay, so that's nice. So that means when I go to my grammar to replace the terminals with the terminating variables, their corresponding terminating variables, then I get something like this. So I replace the two A's with variable A's, these two B's with variable B's, and then the AA and the BB with variables AA and BB. Okay. So, this part of the grammar is nice. It's in CNF, but this part is not. So that means I need to introduce some intermediate variables. So, I'll take x1 here. So I'll get x1 is AA, and I'll get x2 is BB. So then I get the grammar AX1, B X2, and so on. Okay, so this is my grammar now in CNF. Okay, a question which is not in the problem set, but which is maybe relevant is, suppose again I had a CYKS question now, and I said, let's run the CYKS algorithm on using GCNF. So this will be GCNF on the string WAAA. Okay, so let's try this, right? Let's make the table. Actually, let's copy the grammar first. Okay, let's copy the grammar. Now let's make the table. So my string is A. So I make my table like so. And what are my production rules? That's kind of important to know. There are these guys. Okay. And again, I'm going to use the upper triangular part of the table, but feel free to use the bottom. It's the same exact thing. Or the rotation or whatever. As long as you only have one table and one sort of triangular part. Okay, so I'm going to do the sort of base case first. So what are the ways in which I can generate A? So the nice thing here is that the base case is always going to be the same. So the ways for me to generate A, well, there's just one, right? It's A gives you A, right? So I'm going to add A here, and A here, right? Now I do this part of the table. Essentially, what are the ways that I can generate AA? Well, there's two ways now, right? There's S gives you AA, and there's X1 gives you AA. So S gives you AA, so I'll do S and AA, and also X1 gives you AA, so I'll do X1 and A, right? And then again, it's the same thing, right? It's exactly the same sort of case, right? It's just sort of shifted. So S and X1 are the two possible answers here. S gives you AA, and X1 gives you AA. Okay? Now, when I get to the final sort of root node, I have to consider two possibilities, right? Either my grammar generates the string AAA using sort of something like A and then one of these two, or one of these two and then A. Right? So let's see which ones are available to me. Do I have A and S on the right-hand side? No. Do I have A and X1 on the right-hand side? Yes. So already I can stop because that's S, but let's just keep going for the sake of completeness. So the other thing is, do I have S and A? No. And do I have X1 and A? No, right? So the only thing that I seem to have in terms of a parse tree is S. And then, if I follow these yellowish lines, I have A and then X1. So A gives me A here, X1 gives me A here, and then these two A's produce the terminals, right? So this is the parse tree, right? Nice. Cool. Any questions about this? No, it's clear? Can I scroll up a bit? Yes, it's very easy to answer. Yeah?
We would have to do a terminal
Yeah. 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 That's right. Yeah. Yeah, nice. Yeah. So if you had instead something like A gives you AB, or A, right? Then you would have to introduce TA gives you A. You don't touch this one, right? Because this is already in CNF, right? You don't want to introduce a unit production. But you have to do TA, TB here. Yeah, nice. Yeah. Okay, cool. So I have 8 minutes to do the pumping lemma for context-free languages, which means I won't do it, and I will post a video. Yeah, I'll let you go early. I'll post a video very soon because I've already kind of recorded it. I'll see you at the midterm next Tuesday, yes? Next Tuesday. All right, thanks a lot. Yeah, question? Maybe, yeah.